So let's look at this together now then. So let's think about the logic. You help me to decide the start point on this and then what we're going to do. Plan our way through it and then we can do it. So reading the question. So if in doubt, good start point is to draw it and write down what we know in the units that are required. Okay, so that's a good opportunity to jot down everything now with the symbol that is used for it and check it's in the right units. Okay, so write down what we know. We know the mass is 50 kilograms. We know the mean radius is 0.094 meters, putting it in the appropriate unit. We can calculate omega-1 because often we're given the revolutions, the number of revolutions, and it's not uncommon to give it RPM. So we need to multiply the frequency 400 over 60 by 2 pi to get omega-1 and 2 pi times 150 over 60 to get omega-2. So we've got omega-1 and omega-2 and the torque 0.05 newton meters. Now the next thing is, what are we asked to find? So we're asked to find the number of revolutions this thing is going to rotate. During this decelerating period till it comes to a stop. So this thing is decelerating. It's starting off with an omega-2, sorry, a value of omega-1 equal to 40 pi over 3. Then it's decelerating to a speed of 5 pi radians per second. How many revolutions does it go through in that period? Now, we've looked at the question a bit like this when we were looking at angular motion earlier. So what is it, what's the next thing we need to realise to find n? What's it to do with? The key thing to realise is that the number of revolutions equals the total angle turned through, theta, divided by 2 pi. As James says, there's 2 pi radians in a complete turn. So that's the key thing. We're after the number of revolutions. So to find that, we need theta, which is the angle, complete angle it turns through. Think about, I know you weren't here doing the linear motion thing, think about distance travelled. If it had been the total, if I want to find how far it goes in a certain amount of time, then I need the total distance. In angular terms, theta represents effectively the total distance travelled. So this is analogous to the total distance. If I divide the total distance, the total angle, by 2 pi, which is the angle in one revolution, I'll get the number of revolutions. So I'm after theta, which is equivalent to s, displacement in terms of linear motion. So we're after theta. Now we've got to look for a formula that's going to be useful to us that involves theta. So we need to look back at these equations of motion for angle, for angular motion. So there are 3 formulas that include theta. But as you quite rightly pointed out, we don't know the time. So we might have to find the time, but we don't know the time. And in this case, we don't need to find the time because this particular formula, the second one we wrote down here, doesn't involve the time. It involves theta, which we want to find. It involves alpha, which we don't know. So actually, we might end up having to find the time. Okay? And it involves omega-1 we know and omega-2 we don't know. Okay. So, trouble is we don't know alpha. Yeah, and that includes the time. So, what else might we do? What else do we know that might help us here? Right. We know also then that the torque equals alpha I. That also involves alpha. Do we know the torque? Yeah. Do we know I? No, but can we find I? Yeah. So, looks like we've found a root, okay? To be able to use this formula, we needed alpha. And now we found a way of finding alpha, because alpha equals the torque divided by the moment of inertia. So alpha, so what we need is this formula here, rearranged for theta, and then we can find alpha using this. So we know I, in this particular formula, equals mk squared, and as it's a rim flywheel, that's just the radius, mean radius, isn't it, squared, times the mass, and we know the mass. So we can find I. Once we've got I, because we know the torque, we can find alpha, and once we've got alpha in this one, we know omega 1 and omega t, so rearranged we can find theta. Once we've got theta, divide that by 2 pi, and we've got the number of turns. Okay, so I'll pause that there and leave that up. You see if you can finish it off, and we know that the answer turns out to be 1060 because it tells you the answer at the end of the question there. So you should get 1060 at the end. Okay, so final answer then, you should get, to find alpha, putting in the values, we get negative, because it's decelerating, 0.113 radians per second squared. To 3 significant figures, and then to find theta, we have to rearrange this formula for theta. So we subtract omega 1 squared from both sides, divide by 2 alpha, and then put in the values, and we actually end up with a negative divided by a negative, which gives us a positive answer of theta of around about 667.1.9-ish, depending on how you've rounded. And then n equals theta divided by 2 pi comes out to be around about 1062-ish turns. So it's going to revolve that number of times before it comes to a halt.